Tonight, on Space Science, the mission looks clean, precise, and controlled. But Artemis II carries 4 human beings through some of the most unforgiving conditions any crew can face: violent ascent, deep space radiation, the silent far side of the moon, the razor-thin return corridor, and the long chain of systems that must keep working when almost nothing can be allowed to fail. This journey is not just about reaching the moon and coming home. It is about every nightmare scenario NASA trains for, studies, and hopes never becomes real. If this kind of calm, deep space storytelling is what viewers come to Space Science for, please like the video, subscribe, and settle in for the full journey. Before the mission becomes a machine, it is first a place. It begins on a long edge of Florida where land, sea, air, and heat remain in constant motion, and where no launch can ever be separated from the environment that surrounds it. Kennedy Space Center does not stand in a still interior. It stands beside the Atlantic, on low ground exposed to salt air, moisture, shifting winds, and one of the most electrically active weather regions in the United States. The coastline looks open and calm from a distance, but that calm belongs only to appearance. In physical terms, it is a narrow meeting ground between tropical water, sun-heated air, rising moisture, and unstable skies. This is where Artemis II must begin. Long before the crew circles the moon, NASA must first pass through the outer world of weather, and weather is never a passive backdrop. It is one of the oldest sources of danger in spaceflight because it acts on everything at once. It touches the rocket, the ground hardware, the countdown, the timing, the flight path, and the recovery plans that wait on the far side of the mission. Along the Florida coast, warm ocean water feeds the lower atmosphere with moisture. Strong sunlight heats the ground through the day. Air rises, clouds build, and storms can grow with a speed that feels out of proportion to the size of the landscape. Lightning becomes one of the central concerns. It is not only a dramatic flash in the distance, it is electrical structure in the sky, a sign that charge has separated through cloud layers and may discharge through air that suddenly becomes conductive. A launch vehicle does not merely need to avoid being struck directly. It must also avoid conditions in which it could trigger lightning by passing through electrically charged cloud systems. That is why launch weather rules are strict. NASA sets conservative limits for lightning probability, cloud proximity, precipitation, upper-level winds, and electric field conditions. These limits are not signs of timidity. They are acknowledgements that the atmosphere can damage electronics, confuse measurements, threaten structures, and introduce risk before a crewed spacecraft has even left Earth. Wind is quieter than lightning, but it is no less serious. Near the coast, surface winds can strengthen quickly, and winds higher in the atmosphere can differ sharply from those felt on the ground. A rocket rising through the lower atmosphere does not move through one uniform column of air. It passes through layers, each with its own speed and direction. These layered winds can bend loads across the vehicle and create complicated stresses as it accelerates. Even before liftoff, strong winds matter. They influence rollout, fueling operations, exposed hardware, and the basic safety of the launch attempt. The mission therefore begins under a sky that must be measured in detail, not admired from below. Radar, balloons, forecasts, field sensors, and continuous observation all become part of the outer protective shell around the crew. Artemis II has not yet left the ground, but already it depends on interpretation of invisible motion in the air. Rain and hail belong to the same outer problem. Water in the atmosphere does not simply fall, It changes thermal conditions, affects visibility, marks unstable cloud systems, and signals processes that may be linked to stronger hazards. Thick cloud layers reaching into freezing temperatures can support electrical danger. Precipitation through the flight path can challenge launch rules directly. Even temperature becomes operational. Air that is too cold or too hot can alter how systems behave, how materials respond, and how safely the countdown proceeds. The coastline, therefore, does not offer a single kind of risk. It offers a stack of them, layered from sea level upward through cloud, ice, electric field, and high wind. This is the first nightmare region NASA hopes never becomes active at the wrong moment. It is not dramatic because it is exotic. It is dramatic because it is ordinary. The same atmosphere that sustains life can also prevent departure. There is also a broader sky beyond local weather. The sun itself can become part of the launch environment. Severe solar activity can fill near-Earth space with energetic particles capable of disturbing electronics and radio communication. This is still part of the outer region of the mission, because the crew has not yet entered deep space. They remain under the combined authority of Florida weather and space weather, both of which can alter launch decisions. On Earth, danger often arrives as storm cloud or wind shear. Beyond the denser air, danger can arrive as invisible radiation from solar eruptions. NASA watches both. This paired vigilance reveals something important about Artemis II. The mission begins inside nested environments. The crew does not move from safety into danger in one sudden step. They begin in a world already full of conditions that must be judged carefully. The far end of the mission carries its own outer setting. Artemis II does not end on a runway or under a fixed roof. It ends in the Pacific Ocean, where recovery conditions depend on launch day, return geometry, sea state, winds, and distance from land. This ocean region is part of the same outer frame as the Florida coast, because it is another environmental boundary that exists before any spacecraft system is considered in detail. The Pacific recovery zone may be far from shore. It may face rougher water and stronger winds than those used for more routine orbital returns. There is no simple waiting in space for perfect conditions after the flight from the Moon. The broad path home constrains where and when splashdown can occur. That means recovery teams must prepare for uncertainty in weather and sea motion, carrying medical capability, ships, aircraft support, and procedures suited to an ocean landing that may happen far from port. Sea state is a useful term here. It means the condition of the ocean surface, shaped by swell, waves, wind, and local disturbance. A calm sea and a rough sea can change recovery difficulty profoundly. Water motion affects visibility, approach, diver operations, floating hardware, and the stability of the capsule after splashdown. Even after successful re-entry, the mission still depends on the outer natural world behaving within limits that trained teams can manage. The ocean does not care that the hardest work seems finished. It remains what it is moving, heavy, cold, and indifferent. In that sense, Artemis II begins and ends in places that are older than the spacecraft itself. On one side stands the unstable Florida sky. On the other waits the wide Pacific. NASA hopes neither becomes a true nightmare. Yet both are always present, surrounding the mission before any inner layer of technology or human procedure has a chance to matter. At the launch pad, the mission stands upright and motionless, but this stillness is deceptive. The rocket and spacecraft do not wait alone. They remain inside a web of support, checking, supplying, cooling, watching, and confirming. The tower beside them is not a mere frame. It is part of the temporary life of the vehicle before flight. Through it pass power, communication, coolant, purge gases, and the controlled steps that keep Artemis II fit for launch. This region of the mission is neither the open weather of the coast nor the fire of ascent. It is the interval in which a crewed lunar vehicle must remain attached to Earth in exactly the right ways until the instant it must separate from Earth entirely. The mobile launcher and its tower hold much of this burden. From a distance, the structure appears rigid and architectural, almost permanent. But its real purpose is dynamic. It supports the stack, gives access to different levels, and carries the umbilicals that connect ground systems to the vehicle. An umbilical is a service connection that feeds a rocket or spacecraft while it still stands on the pad. These lines and interfaces provide electricity, data links, gases, propellants, and thermal support. They also represent vulnerability. Every line must function properly while attached and then separate cleanly. A connection that fails too early can starve a system before liftoff. A connection that fails too late can resist departure. For this reason, the quiet interfaces between vehicle and tower become one of the most serious places in the countdown. The nightmare here is not dramatic in appearance. It is a seal that does not hold, a valve that does not open as expected, a sensor that disagrees with another sensor, a quick disconnect that does not behave exactly as required. Cryogenic loading makes this danger sharper. Artemis II depends on extremely cold liquid hydrogen and liquid oxygen, carried into the core stage and upper stage through ground equipment and umbilical systems. These propellants are valuable because they deliver strong performance, but they are also difficult companions. Liquid hydrogen is especially demanding. It is cold enough to shrink materials, thin enough to escape through small imperfections, and light enough to turn a minor leak into a serious concern. Liquid oxygen is also highly reactive and must be handled with care. During tanking, the launch vehicle passes from being a complicated machine into a machine filled with substances that boil easily, build pressure, and require constant management. This is why the countdown is not a simple clock running towards zero. It is a controlled negotiation with temperature, pressure, flow, and timing. NASA builds holds into the countdown for this reason. A hold is an intentional pause. The clock stops so teams can review conditions, complete tasks, and decide whether the mission should proceed. These pauses are not inefficiency, they are structure. They create time for human judgment inside an operation otherwise governed by strict sequence. Roughly 2 days before liftoff, teams begin arriving at their stations, powering major systems, preparing the liquid oxygen and liquid hydrogen flow paths, and bringing the spacecraft and rocket stages to life in stages rather than all at once. Batteries are charged, engines are readied. The upper stage is powered, then later powered again for launch. Non-essential personnel leave the pad well before the final hours. Each of these moments narrows the mission. Each removes flexibility. The tower also carries the human path to the spacecraft. Near the top sits the crew access arm, ending at the White Room, the environmentally controlled space where astronauts enter Orion, and where the close-out crew completes its final work. This place is calm by design. It is clean, contained, and procedural. Yet it is also one of the most fragile points in the pre-launch chain, because the mission is now reduced to hatches, seals, fasteners, suits, air quality, and direct human handling. The close-out crew inspects hatch surfaces, checks seals, verifies environmental conditions, and confirms that the spacecraft is properly closed for flight. These are small actions in physical scale, but they carry immense consequence. A hatch is only a boundary. Its success depends on precision. The wrong particle, the wrong alignment, or the wrong reading can turn a sealed spacecraft into an unsafe one. Even after the crew is inside, the vehicle does not become self-sufficient. It still relies on ground support. Propellant tanks enter topping and replenish operations because cryogenic liquids naturally warm and boil away even inside insulated systems. To keep the rocket in launch condition, teams continue feeding small amounts of propellant and managing pressure. That means the vehicle on the pad is never fully still in a practical sense. Inside lines and tanks, fluids move, pressures change, valves cycle. Computers compare expected values with actual values. People watch for anything that drifts beyond limits. A launch attempt can therefore be halted by something that never becomes visible to the eye. This is why countdown culture is conservative. Artemis II cannot operate on the pad with small uncertainties left unexplained. The vehicle is tall, fueled, crewed, and attached to a network of temporary supports that must all keep working until they must all stop working in a very precise order. The launch team must trust hardware, software, instrumentation, procedures, and one another. Yet trust in this setting is never blind. It is repeatedly tested against measurement. If temperatures sit outside limits, if lightning probability rises during tanking, if hazardous gas sensing points to a leak, if a battery does not reach the right condition, if the hatch area does not remain safe for the closeout crew, the sequence must stop. The mission does not earn liftoff by desire. It earns liftoff only by satisfying constraint after constraint after constraint. That is the unsettling character of the pad and countdown region. The rocket appears strongest here because it is fully assembled and nearly ready, but this is also when it is most dependent. It stands on the threshold of independence while still drawing on Earth for almost everything. Fuel comes from below, power comes through lines, cooling and purge flows come through interfaces, human access comes across the arm, safety comes from rules, not momentum. NASA hopes the tower remains merely a place of orderly departure. It hopes the countdown remains a disciplined march of expected events. The nightmare scenario is that something small inside this temporary dependence refuses to behave, and that the still vehicle on the pad becomes the most dangerous form it can take, not a spacecraft in flight, but a spacecraft almost ready to fly. When the countdown reaches its end, the quiet dependence of the pad gives way to a brief and violent passage through air. This is the ascent region, where Artemis II must move from a standing structure into a flying one, and where the outer atmosphere becomes an active physical force on every surface, joint, instrument, and human body inside Orion. The rocket leaves the ground with immense thrust, but thrust does not erase vulnerability. It only begins a new form of it. At liftoff, the Space Launch System rises with more than 8 million pounds of thrust, while its two solid rocket boosters provide most of the power needed in the opening part of flight. The vehicle is heavy, loud, and accelerating. Yet the danger in this interval comes from the fact that it is still deeply embedded in Earth's lower air. It must force its way upward through density, pressure, cross-flow, vibration, and heat generated not by return from space, but by moving at extreme speed through an atmosphere that resists being crossed. The first nightmare scenario NASA hopes never faces here is simple in concept, and severe in meaning a major problem, while the spacecraft is still too low for spaceflight to protect it, and too high for the ground to help it. Air behaves like structure at these speeds. Near the pad it is thick, higher up it thins, but during the first minutes of ascent the vehicle passes through a changing column that presses on the rocket unevenly and continuously. Engineers speak of dynamic pressure, which means the aerodynamic force created by moving through air. There is a part of ascent when this pressure reaches a peak, and that period is one of the most demanding moments of the climb. The rocket is accelerating hard. The air is still thick enough to matter greatly, and the vehicle must remain stable despite buffeting, acoustic loading, and structural strain. Nothing visible from the crew cabin may seem to explain the severity of this moment. The sky outside can appear open and clear, yet the rocket is then inside one of the harshest mechanical environments of the entire mission. It is being bent, shaken, and driven upward through a fluid medium that punishes small weakness. If a sensor begins to disagree with reality, if a control response drifts, if a propulsion problem appears, or if structural behavior departs too far from prediction, the mission can move in seconds from ascent to emergency. This is why ascent is not merely a powered climb. It is a narrow envelope, meaning a limited band of acceptable conditions, inside which speed, attitude, loads, and timing must remain under control together rather than one by one. For the crew, the existence of a launch abort system defines the seriousness of this region. Orion carries a dedicated escape tower above the crew module because NASA accepts that the earliest part of launch is the part least forgiving of severe failure. The system is built to act within milliseconds if an emergency demands it. Its purpose is not to save the whole spacecraft. Its purpose is to pull the crew module and the astronauts inside away from the rocket fast enough to outrun disaster. The design uses 3 solid rocket motors working in sequence and in cooperation. The abort motor supplies the sudden force that yanks the capsule clear. The attitude control motor steers and orients the escaping vehicle. The jettison motor then separates the escape tower from the crew module before parachute descent. This system exists because a failing launch vehicle does not provide much time for thought. It provides almost no time at all. The escape decision must be made inside a moment when heat, debris, pressure, and loss of control may all be growing together. NASA tested this architecture before Artemis II because crew survival in ascent cannot depend on theory alone. The nightmare here is the very situation the escape tower is meant for a serious booster, engine, or guidance emergency during the part of flight, when Orion still needs a dedicated mechanism to get clear. Even the shape of the abort system reveals how severe the ascent region is. The tower sits above Orion, not below it, because the fastest path to safety is to pull the crew module away from danger rather than try to push the whole spacecraft from underneath. In a normal launch, this escape system is temporary. It protects Orion through launch and ascent, and once the rocket climbs above most of the atmosphere, its job is finished. NASA then throws it away because carrying thousands of pounds of no longer needed hardware deeper into space would only burden the mission. The recent Artemis II launch day updates show this clearly in practice. The twin solid boosters separate after roughly the first 2 minutes, and soon after, with the vehicle above the densest layers of the atmosphere, the fairings and launch abort system are jettisoned. That sequence captures the logic of the ascent envelope. Early on, Orion needs extra shielding against heat, wind, acoustics, and catastrophic rocket failure. Later, once the air grows thinner and the spacecraft no longer faces the same aerodynamic punishment, that protection becomes expendable mass. The dangerous beauty of ascent lies in this transformation. For a brief time, the mission is enclosed inside emergency hardware because the surrounding conditions justify it completely. Then, if all goes well, that outer shell is discarded almost as suddenly as it was needed. Inside Orion, the crew experiences this region not as open sky, but as acceleration, restraint, vibration, sound, and disciplined procedure. They do not control the environment in any ordinary sense. They ride through it while the rocket and spacecraft execute the planned climb. The ascent region therefore compresses an enormous amount of physical risk into a short span of time. The vehicle must clear the tower, survive maximum aerodynamic loading, maintain healthy propulsion, separate boosters cleanly, protect the crew against the acoustic and thermal violence of launch, and preserve an escape path in case something goes badly wrong before the atmosphere loosens its hold. NASA hopes this entire interval remains almost uneventful in outward appearance, a clean rise, a bright plume, a sequence of successful separations. Yet beneath that outward simplicity lies one of the most unforgiving portions of the mission. Here the crew is still close to Earth, but closeness brings no comfort. Earth is not shelter in this moment. Earth is air, gravity, and force, and Artemis II must pass through all three before the mission can become anything calmer than survival through ascent. Once ascent ends and the violence of the lower atmosphere falls away, the mission enters a region that looks far calmer from the outside. Orion is now in space, the crew is alive and weightless, and Earth remains close enough to fill the windows with something larger than a distant world. Yet this early orbital phase is not a place of rest. It is a proving ground. Artemis II does not leave Earth immediately for the Moon. It first spends time in Earth orbit because NASA wants the spacecraft and the crew tested while home is still near in relative terms. The mission circles Earth twice, first in a stable low orbit and then in a much higher elliptical orbit, so that the crew and flight controllers can confirm that Orion behaves as expected before the spacecraft commits to a deeper path outward. This is the region where relief can become deceptive. The rocket has done its work, but the spacecraft has not yet earned trust. The first part of this orbital period is shaped by geometry. Orion begins in an early orbit that is then refined by upper stage burns. The interim cryogenic propulsion stage raises the low point of the orbit to a safe altitude and then raises the high point much farther, placing Orion into a high Earth orbit that gives the crew time and space to test the spacecraft while still remaining within the wider neighborhood of Earth. This arrangement is deliberate. It creates distance from the immediate hazards of launch, but it does not yet surrender the advantages of nearness. In a mission of this kind, that matters. The spacecraft is crewed for the first time in the Artemis program. Its systems must prove themselves in the real environment of space, not in the shelter of ground testing, and not yet in the remoteness of the translunar path. The nightmare scenario here is not sudden explosion, but hidden underperformance. A spacecraft can look healthy after launch and still carry faults that only become visible when its life support, navigation, power, and thermal systems work together over time in orbit. After the upper stage has done its job, Orion separates and the mission enters one of its most distinctive early demonstrations. The crew uses the detached upper stage as a target for manual proximity operations. This means the astronauts guide Orion through controlled approach and retreat maneuvers near another spacecraft-like object. Using onboard navigation sensors and reaction control thrusters, while flight controllers watch from Earth. The purpose is practical. Future Artemis missions will require rendezvous and docking work in lunar space, and some of the needed skill can only be tested properly in flight. The upper stage becomes a temporary stand-in for those later partners, yet the calm logic of the test does not remove the risk inside it. Orion is now a piloted spacecraft flying near a recently separated stage, and every approach must remain measured, every retreat deliberate, every orientation change understood. A spacecraft in close proximity to another object is no longer protected by distance. Even small relative motion matters. A poor sensor reading, a navigation misunderstanding, a thruster response not quite matching expectation, or a crew workload issue could turn a useful demonstration into an avoidable emergency. NASA therefore treats this not as a display of confidence, but as a controlled examination of how Orion and its crew behave when precision matters more than speed. This early flight region also reveals a quieter source of danger, the difference between surviving launch and being ready for deep space. Orion must prove that it can maintain breathable air, control cabin conditions, manage power, navigate correctly, and communicate through changing network conditions. While still in Earth orbit, the crew evaluates the systems that generate and preserve the internal environment they need to remain alive. Air is not merely present or absent. Inside a spacecraft, it must be circulated, conditioned, monitored, and kept within narrow limits for pressure, composition, and temperature. Thermal control is equally constant. A spacecraft passing in and out of sunlight can warm and cool unevenly, and the internal balance must remain stable despite those outer changes. In this region of the mission, NASA wants such processes tested while the crew remains comparatively close to Earth, because this is the last phase in which problems can be found before the spacecraft tries to move beyond Earth orbit. The nightmare scenario is therefore intimate rather than spectacular. It is a cabin that drifts away from expected conditions, a system that vents more than predicted, a display that does not agree with the sensor, a procedure that takes too much effort, or a fault light that turns a routine checkout into a chain of troubleshooting. Navigation and communication are part of the same proving ground. In ordinary Earth orbit, spacecraft often rely on familiar networks and the reassuring closeness of the planet below. Artemis II deliberately stretches beyond some of that comfort. During this orbital period, Orion briefly moves beyond the range of the Global Positioning System and the relay satellites of NASA's near-Earth network, so that the mission can check the deep space network and related communication and navigation capabilities early, before departure from Earth orbit. This is a quiet but important test. It asks whether the spacecraft and the ground can work together when the mission begins behaving less like low Earth flight and more like deep space flight. If that handover is imperfect, uncertainty enters the mission in one of the worst possible ways, not as visible damage, but as degraded awareness. A spacecraft that is healthy but poorly understood can still become dangerous, because time and fuel can be spent solving confusion instead of preserving margin. So this high Earth orbit region becomes a last careful circle around home rather than a simple waiting room before the moon. The crew is already far above ordinary orbital life, yet still close enough to Earth for every weakness to matter with special urgency. The spacecraft must separate cleanly, fly manually with precision, sustain its cabin, prove its displays and controls, and show that its communications and navigation can cross the threshold from near-Earth practice toward deep space reality. NASA hopes this region remains methodical and almost uneventful. It hopes the crew sees Earth not as a warning, but as a nearby companion during a disciplined test. Yet beneath that quiet hope lies the central fear of this phase, that the first crewed days of Orion in space might reveal not one fatal flaw, but several small mismatches between expectation and reality, each manageable alone, yet together enough to make the mission feel uncertain, while Earth is still close enough to remind everyone what has not yet been lost. The mission changes meaning at the moment Orion stops merely circling Earth and begins to leave Earth behind. This is the region of the translunar injection burn, the engine firing that turns a cautious orbital test flight into a true lunar voyage. Until this point, Artemis II remains in a condition that still belongs to Earth. The crew is already in space, already weightless, already dependent on Orion alone for life and function, but the spacecraft is still moving within an Earth-shaped pattern. The translunar injection burn breaks that pattern. NASA describes it as the last major main engine firing of the mission, the burn that places Orion on the path toward the Moon, and at the same time sets the spacecraft onto the free return trajectory intended to bring the crew back to Earth for splashdown. In that sense, the burn is not only a departure, it is also the beginning of the return, folded into one act of propulsion and geometry. That dual meaning makes this one of the most unsettling regions of the flight. A burn is not simply a burst of power. It is a timed and directed change in velocity, and velocity in space is destiny. The main engine does not push Orion toward a visible road. It alters the spacecraft's motion so precisely that gravity itself takes over the rest of the larger path. Orion must be in the proper alignment with Earth and the Moon when the burn occurs. The burn must last long enough, point in the correct direction, and remain stable throughout. If it underperforms, the spacecraft may not gain the needed energy to depart Earth as planned. If it overperforms or points imperfectly, the trajectory may drift away from the intended corridor. Space does not absorb such errors kindly. There is no atmosphere to smooth the path and no road to follow back. A spacecraft either enters the correct path through precise motion, or it does not. NASA's own mission materials make clear how central this event is. The translunar injection burn sends Orion toward the Moon and establishes the free return path that uses lunar gravity to send the spacecraft home without additional major propulsive maneuvers. The phrase free return sounds gentler than the reality it describes. It does not mean effortless safety. It means the trajectory is shaped so that if later major propulsion is not available, the spacecraft can still loop around the Moon and come back toward Earth. This is an old and elegant idea in lunar mission design, but elegance does not remove tension. The free return path is not a soft rescue net hanging beneath the mission. It is a narrow gravitational arrangement created by the right burn at the right time. Orion does not simply wander into it by being near the Moon. The spacecraft must be placed there. That is why the translunar injection burn feels like a threshold more serious than launch in one specific way. Launch demands survival through force. This burn demands correctness through precision. The violence is lower, but the commitment is deeper. Once Orion leaves Earth orbit on this path, the mission is no longer rehearsing deep space. It is living inside it. The engine responsible for this change sits in the European Service Module, the part of Orion that provides propulsion, power, and support functions behind the crew module. In this region of the mission, the quiet machinery of the service module becomes decisive. The main engine has already existed as a trusted capability through launch and orbital checkout, but now it becomes the single instrument that must transform the spacecraft's future in one deliberate event. NASA's recent mission updates describe the crew as becoming truly bound for the Moon only after this burn succeeds. That language matters. Before the burn, the mission still holds onto Earth by orbital logic. After the burn, Orion carries the crew into a path that will take them around another world. The nightmare NASA hopes never sees here is not only total engine failure, it is any condition in which the burn begins to depart from expectation while the spacecraft is committing itself beyond easy correction. A rough ignition, unstable thrust, an attitude problem, a guidance mismatch, or an unexpected cutoff would all threaten the mission in a region where small errors grow into large consequences. There is also a temporal strangeness in this part of the flight. The translunar injection burn happens early, only about 2 days into the mission, yet NASA notes that it essentially doubles as Orion's deorbit burn as well. This does not mean the spacecraft is turning around at once. It means the mission's broad return logic is embedded from the beginning of the lunar departure. The same decision that sends Orion outward also determines the shape of the path that will eventually bring it back. That is a sobering kind of economy. The crew is not merely asking the spacecraft to go somewhere far away. They are asking one burn to set the terms of absence and homecoming together. Such design reflects confidence in orbital mechanics, but it also reveals how little room exists for casual improvisation once the mission commits to its deep space line. After this burn, smaller trajectory correction burns remain available as needed during the outbound passage, and communication support transitions primarily to the deep space network as Orion leaves the nearer operational habits of Earth orbit. These facts are reassuring on paper because they show that the mission is not abandoned to one single moment forever. Yet the reassurance has limits. Small correction burns can trim a path, not redeem every major failure in the burn that truly matters. Communication links can keep mission control informed, but information cannot replace missing energy or undo a badly shaped departure. The free return concept exists because lunar flight respects geometry before hope. NASA builds margin where it can, but margin must still begin from a trajectory close enough to the intended one for the laws of motion to remain helpful rather than hostile. So this region is quiet in appearance and severe in meaning. No tower falls away here, no ocean waits below, no bright atmospheric fire surrounds the spacecraft. Orion seems almost serene, suspended against darkness, with Earth slowly becoming less central behind it. Yet in engineering truth, this is one of the sternest commitments of Artemis II. A single major engine firing must be timed, aimed, and completed with exactness so that the spacecraft leaves Earth orbit, reaches the Moon's realm on the correct line, and carries within that outward motion the promise of return. NASA hopes this moment remains as clean as its ideal description suggests: a successful burn, a good trajectory, a spacecraft now genuinely on its way. The nightmare it hopes never happens is that the mission crosses this threshold imperfectly, because beyond this point the path itself becomes the spacecraft's greatest ally only if it is entered correctly in the first place. Beyond the broad magnetic shelter of Earth, space becomes outwardly quiet and physically severe. This is the deep space region that Artemis II is built to enter after leaving Earth orbit, and it is one of the clearest examples of danger arriving without spectacle. Earth's magnetosphere, the vast magnetic field that surrounds the planet, traps and deflects many charged particles that would otherwise move more freely through near-Earth space. Inside that protection, radiation remains a concern, but it is moderated. Outside it, the balance changes. NASA describes Artemis II as the first human mission in more than half a century to go beyond this protective magnetic field. That fact gives the region its true character. The crew is not merely travelling farther. They are crossing from a partially sheltered neighbourhood into a harsher one, where the surrounding space itself becomes a source of risk. The danger is not only that space is empty, it is that emptiness removes buffers that life on Earth takes for granted. There is no air pressure outside Orion, no breathable oxygen, no medium to carry away heat by ordinary convection, and no natural shield comparable to the atmosphere below or the magnetosphere around Earth. Vacuum does not attack like wind or fire, yet it makes every protective layer of a spacecraft essential. A thin boundary must keep pressure inside and nothingness outside. Every seal, window, and structural surface matters because there is no forgiving environment beyond them. In deep space, the crew cannot depend on nearby orbital infrastructure, cannot step into safer air, and cannot draw on any surrounding environment to help stabilize life. This is why the deep space coast toward the Moon feels so unsettling in physical terms. The spacecraft appears to move through emptiness, but the emptiness is itself one of the mission's defining hazards. Orion is designed for this regime, yet design does not make the environment gentle. It only makes survival within it possible. Radiation gives this quiet region its sharpest edge. In deep space, the main sources are high-energy particles from the Sun, and energetic particles from cosmic rays arriving from beyond the solar system and, in NASA's older descriptions, beyond the galaxy. These are not rays in the sense of visible beams crossing the cabin. They are particles moving with enough energy to damage living tissue and disrupt electronics. NASA explains that such radiation can affect both cells and hardware, while ESA notes that exposure beyond the magnetosphere can rise far above what astronauts experience aboard the International Space Station, and many times above what people experience on Earth's surface. Most of the time, this threat is invisible. A spacecraft window will not reveal it. The crew can sit in apparent calm while a dangerous environment passes through the walls in ways only instruments can measure. That invisibility is part of what makes this region so difficult. A threat that can be seen can often be avoided by instinct. A threat that must be inferred from detectors, forecasts, and physics requires constant vigilance even when nothing outward seems wrong. Solar activity is the most immediate reason NASA watches this region so closely. A solar flare is a sudden burst of energy from the Sun, and a coronal mass ejection is a large release of solar material and magnetic field into space. Either can be associated with solar energetic particles that move fast enough to become dangerous to crews traveling beyond Earth's magnetic protection. NASA and NOAA plan to monitor the Sun around the clock during Artemis II, using real-time data from multiple solar observatories and warning the mission team if conditions suggest particles may cross Orion's path. The concern is not abstract. NASA notes that a significant solar particle event near the crew could raise radiation levels inside the spacecraft, while ESA warns that a severe event of the kind seen in the early 1970s would be a serious medical threat to astronauts outside Earth's magnetic protection. The nightmare scenario here is therefore not a broken spacecraft at all. It is a healthy spacecraft suddenly finding itself in the path of a violent solar event that no wall can completely erase. Because of this, Artemis II treats measurement as a form of protection. Radiation trackers will fly with the crew and inside Orion, and NASA plans to use personal dosimeters carried by the astronauts to measure exposure in real time. Additional monitors will be placed at different shielding locations inside the cabin, so the mission can learn how radiation varies from one spot to another, and so the crew can be warned if conditions suggest they should move into a better protected configuration. Artemis II is not only a voyage around the Moon, it is also a scientific campaign to characterize the deep space radiation environment for future missions. NASA's human research plans for the flight include radiation studies, biological investigations using human cell-based devices, and related measurements intended to improve protection for later crews. This reveals something fundamental about the region itself. Deep space is still only partly known from the standpoint of human exposure. The mission is designed not just to endure the environment, but to understand it more directly than any crewed American lunar flight has done in decades. Protection in this region is therefore layered rather than absolute. Orion is designed from the start to preserve the reliability of essential systems during radiation events, and both NASA and ESA describe the spacecraft walls as blocking much of the radiation from a particle event. Yet neither agency describes this as perfect safety. Instead, they describe procedures, monitoring, and the possibility of sheltering. Orion includes the concept of a temporary storm shelter within the crew module, created with onboard materials and equipment to increase shielding if solar conditions demand it. Artemis II's current mission planning even includes a crew exercise in which the astronauts assess their ability to build such a shelter for use during a high radiation event. This is a calm but revealing detail. In the deep space region, protection is not only built into hardware, it may also depend on crew action, speed of response, and the intelligent use of whatever mass and materials are available inside the spacecraft at the moment danger rises. There is a second unsettling truth in this region. Radiation is not the only consequence of leaving Earth's protective shell. Communication and navigation also change character. Orion transitions to the Deep Space Network for communications beyond low Earth orbit, because the ordinary near-Earth architecture is no longer enough. In practical terms, this means the mission is moving into a zone where distance, signal timing, and self-reliance matter more, even when the crew is well, and even when the spacecraft remains healthy. Deep space reduces the sense of immediate connection with home. The outward environment is harsher, the protective field of Earth is behind them, and the operational support structure becomes more stretched. None of this means the crew is abandoned. It means the mission is now living by systems meant specifically for deep space, because ordinary orbital habits no longer apply. The vacuum outside and the radiation passing through it are only part of the story. The whole region makes the spacecraft feel more solitary. So this part of Artemis II is defined by an unusual combination of calm appearance and strict physical danger. Orion will seem to drift through darkness in silence, with Earth no longer providing the same magnetic shelter it offered before. The cabin will remain pressurized. The crew will work, eat, sleep, and monitor their systems, and the flight may look composed from the inside. Yet surrounding that normality is an environment that can harm tissue, challenge electronics, and change with little visible warning. NASA hopes this region remains quiet, its radiation levels manageable, its forecasts uneventful, and its shelter procedures merely precautionary. But the nightmare scenario it hopes never occurs is written into the region itself, a human crew moving through deep space in a spacecraft that must hold back vacuum, track invisible radiation, and trust constant watchfulness against a sun that does not need to look dangerous in order to be so. By the time Orion reaches the Moon's neighborhood, the mission has already survived launch, checkout, and the long outward passage through deep space. But the lunar flyby introduces a different kind of danger, one built not around raw exposure or engine commitment alone, but around precision in motion. The spacecraft does not arrive at the Moon as an aircraft arrives at a runway. It arrives on a gravitational path that must be shaped with care well before the Moon fills the windows. NASA's current mission planning places 3 outbound trajectory correction burns along the way, with the final one occurring on the day before the flyby, because the spacecraft must reach the Moon on the right line, at the right time, and with the right attitude if the swing around the far side is to do what the mission requires. This is the region where navigation becomes almost architectural. Small differences in timing or direction can alter what the Moon's gravity does to Orion, and the Moon is not forgiving simply because it is familiar in the sky. It is a massive body with an uneven gravitational field, no atmosphere to cushion error, and a narrow role in the Artemis II mission. Orion is not meant to enter lunar orbit on this flight. It is meant to pass by, close enough for the Moon to bend the trajectory home, but not so close that the mission slips outside the corridor set by the free return design. This is why the approach is corrected in stages rather than trusted to one perfect departure from Earth. A trajectory correction burn is a small engine firing used to refine the path, and Artemis II uses several on the way out because navigation into lunar space depends on continuous knowledge rather than initial confidence alone. Orion relies on its guidance, navigation, and control system, on tracking from Earth, and on onboard sensors that include star trackers and an optical navigation camera in the broader Orion design. The purpose of this arrangement is not luxury, it is resilience. A crewed spacecraft passing the Moon on a free return path cannot afford to misunderstand where it is, how fast it is moving, or how its orientation relates to the planned flyby geometry. NASA's own technical work on Orion navigation notes that backup logic, burn placement, and even the effects of spacecraft venting all matter when designing the correction strategy for Artemis II. The nightmare scenario in this region is therefore not only a large failure, it is a navigation chain that begins to drift slightly from truth while remaining plausible enough to tempt confidence. A burn that is a little late, a state estimate that is a little wrong, or a sensor interpretation that is a little less accurate than believed can remain quiet for hours and still matter greatly by the time the spacecraft reaches the far side of the Moon. As Orion crosses into the lunar sphere of influence, the physical meaning of the mission changes again. NASA defines this as the point where the pull of the Moon becomes stronger than the pull of Earth, and that transition happens on the day before the flyby. The spacecraft is then no longer simply approaching the Moon in a descriptive sense. It is entering a zone in which the Moon becomes the dominant nearby mass-shaping motion. From there, the line of travel must remain disciplined. Current NASA mission material says the crew will pass within roughly 4,000 to 6,000 miles of the lunar surface on the far side, while other official Artemis II visualizations give a mean far-side flyby altitude a little above 4,000 miles and note that the exact geometry varies with launch day and time. That variability is important. The mission does not fly through one eternal and identical corridor. It flies through a family of allowed corridors, all of which must satisfy power, thermal, communication, and return requirements. NASA has stated that launch opportunities are ruled out if the resulting trajectory would place Orion in eclipse too long, because the solar arrays must still receive enough sunlight to generate power and maintain thermal balance. The Moon pass, therefore, is not only about missing the surface. It is about satisfying a wider set of constraints all at once, while one world's gravity hands the spacecraft back toward another. The far side itself adds another layer of difficulty. As Orion swings behind the Moon, NASA expects a communications loss of roughly 30 to 50 minutes. This is normal, but normal does not mean trivial. A spacecraft behind the Moon is hidden from direct radio contact with Earth by the Moon's own bulk. During that interval, flight controllers cannot speak with the crew in real time, and the crew cannot rely on immediate exchange with the ground, while the spacecraft passes through the most symbolically important portion of the flyby. The mission is designed for this. The crew prepares observations in advance, records them as they happen, and continues working through the blackout so the information can later be connected with the images and timing of the pass. Yet the communication gap still sharpens the sense of isolation. It means that the region of closest partnership between Orion and the Moon is also the region where Earth briefly falls silent. If a severe problem appeared during that interval, the crew would first meet it alone. The fear NASA hopes never becomes real here is not merely loss of voice contact. It is the coincidence of silence with anomaly, a moment when a navigation concern, attitude issue, sensor disagreement, or unexpected systems behavior appears while the spacecraft is behind the Moon, and the ground can do nothing except wait for signal to return. There is also a quieter human dimension to this region. NASA's daily mission planning shows that the crew devotes much of flyby day to observing, photographing, and describing the lunar surface. including areas no human eyes have seen directly from this perspective in more than half a century. Those activities sound observational, but they are tied to navigation and operational awareness as well. The crew studies geography targets in advance because lighting conditions depend on the exact launch time and on the sun's angle over the moon when Orion arrives. Under high sun, shadows fade and relief becomes harder to judge. Under lower sun, ridges, crater rims, and slopes stand out more strongly. In either case, perception changes with geometry. A world that appears simple from far away becomes complex when seen at flyby distance. And complexity is never neutral for a crew that must remain aware of spacecraft attitude, windows, glare, target orientation, and timeline discipline. NASA notes that Artemis II may also set a new record for the farthest distance humans have travelled from Earth, depending on the launch day. That fact does not make navigation harder by itself, but it deepens the meaning of the moment. The crew is not only near the moon, they are as far from Earth as human beings may ever have been, moving on a line that must be correct because there is no lunar orbit insertion planned to soften the encounter into a prolonged stay. The moon comes close, bends the path, and lets go. NASA hopes the sequence remains exactly that clean a final outbound correction, a controlled far-side passage, a brief communication blackout, and a successful reappearance on the homeward line. The nightmare it hopes never happens is that the flyby geometry proves even slightly wrong at the one place in the mission, where another world briefly takes over the steering. The return to Earth is not a simple fall home, it is a corridor. And the word corridor matters because it implies a narrow path with hard boundaries on both sides. By the time Artemis II turns back from the moon, the great burn that sent Orion outward has already fixed much of its fate, and the long coast home becomes a process of refining the exact point at which the spacecraft will meet the atmosphere. NASA describes this as setting up entry interface from roughly 250,000 miles away, a demand for precision that sounds almost unreasonable until it is remembered that the atmosphere is thin compared with the scale of the journey. Orion is not aiming for Earth in a general sense. It is aiming for one acceptable doorway into Earth's air. If that doorway is reached too shallowly, the capsule can skip off the atmosphere and head back out into space. If it is reached too steeply, the vehicle can be overstressed by the loads of return. This is the nightmare region NASA hopes never misjudges, because the spacecraft is no longer merely returning to Earth. It is trying to arrive at Earth in exactly the one way that allows survival from lunar speed. That narrowness becomes more unsettling because Orion does not simply plunge straight down. NASA's current understanding of Orion return, shaped heavily by Artemis I, depends on skip entry guidance. In plain terms, the capsule first dips into the upper atmosphere and uses drag to shed part of its speed, then uses its lift to rise back out briefly before entering again for the final descent. This maneuver is not theatrical, it is functional. NASA explains that the skip provides more flexibility by extending the range Orion can fly after the point of re-entry to reach its landing area in the Pacific, and it is also needed for the speeds expected on lunar return missions. That means the entry corridor is not just narrow in angle, it is dynamically narrow across time. The first dip, the brief climb back out, and the second descent must all work together in the right sequence. A capsule that arrives from the moon is too fast for a casual meeting with the atmosphere. It must negotiate with the air in stages, and the atmosphere becomes part of the guidance system, whether the crew can see that clearly from inside or not. The fear here is not only missing Earth, it is entering correctly at first, and then letting the skip behavior drift outside what the guidance system and aerodynamics are meant to manage. Before Orion reaches that corridor, the spacecraft must shed part of itself. NASA's mission planning states that the European service module is jettisoned about 20 minutes before entry interface, leaving the crew module free-flying by itself for the first time and turning its heat shield into the direction of travel. This is a quiet separation, but it carries a severe meaning. Until then, the service module has been the engine room, support structure, and propulsion source guiding Orion through deep space. At entry, that support must disappear so the crew module can become the only surviving body of the spacecraft. Entry interface itself begins high above the planet, at about 400,000 feet in the NASA mission description, which is high enough that the atmosphere still seems almost absent, and yet dense enough to matter immediately at lunar return speed. From that point onward, the environment ceases to be deep space vacuum and becomes a compressing shell of gas that grows stronger second by second. A spacecraft that was built for emptiness must now trust the atmosphere to slow it without destroying it. That reversal is one of the strangest truths of a lunar flight. The same Earth that once held the mission down with gravity now becomes the only available medium capable of taking away enough speed to let the crew live. Inside that corridor, heating, ionization, and deceleration arrive together. NASA has said Orion returns from the Moon at about 24,500 miles per hour, around Mach 32, and that temperatures outside the heat shield can approach nearly 5,000 degrees Fahrenheit. At such speeds, the air in front of the capsule is compressed and heated into plasma, a superheated ionized gas that can interfere with radio transmission. NASA's Orion re-entry material from earlier flight testing describes how this plasma surrounds the vehicle and prevents downlink at the key point of descent, while mission management descriptions note a blackout period during re-entry before the spacecraft emerges into peak aerodynamic loading. This silence is different from the planned communications loss behind the Moon. That earlier silence comes from celestial geometry. This one comes from the physics of returning too fast through air for ordinary radio contact to survive uninterrupted. The crew can still act, but the spacecraft becomes briefly harder for Earth to hear. At the same time, the body endures rising loads as speed is stripped away. Return from low Earth orbit is already severe, but NASA stresses that lunar return is harder, faster, and hotter. The nightmare scenario here is not simply heat by itself. It is heat, plasma, deceleration, and brief isolation all arriving together at the very moment the vehicle must remain most stable. This region also carries the memory of Artemis I. After that mission, NASA found unexpected char loss on Orion's heat shield. The agency later determined that gases generated inside the Avcoat ablative material were not venting as expected during skip entry, allowing pressure to build, crack the char layer, and break off some of the outer material. NASA also stated that the Artemis I flight data showed that a crew would have remained safe, and that the agency could keep Artemis II's crew safe using the current heat shield with operational changes to entry. That finding adds a particular weight to the return corridor for Artemis II. The corridor is not only a matter of old Apollo-like heritage or broad engineering confidence. It is a region recently re-examined because real flight taught NASA that its earlier ground understanding was incomplete in one important detail. The return path home therefore becomes both a mission phase and an argument with experience. Orion must enter at the right angle, perform the skip correctly, endure plasma blackout, and slow from lunar velocity inside an operational strategy refined by what the previous flight revealed. NASA hopes this entire passage remains mathematically quiet and physically exact. It hopes the crew crosses the corridor as if moving through a door designed precisely for them. The nightmare it hopes never happens is that the door proves even slightly narrower than expected, because at this speed, there is almost no difference between arriving at Earth and arriving at it wrong. After the corridor of re-entry has been crossed, the mission does not end on solid ground. It ends in the Pacific Ocean, and that gives the final phase of Artemis II a character different from the finality people often imagine in a spacecraft return. Orion does not descend toward a runway. It descends toward moving water. NASA's current Artemis II mission profile says the capsule will splash down in the Pacific and that the crew and spacecraft will be recovered with help from the U.S. Navy. The parachute sequence is only the beginning of this region, not its completion. After the forward bay cover is cast off, the drogue parachutes and then the 3 main parachutes slow Orion to splashdown speed. But even a correct landing does not guarantee the vehicle's first posture in the water. The crew module may land upright, upside down, or on its side. For that reason, Orion carries a system of 5 orange airbags around the top of the spacecraft so the capsule can be brought into an upright position for safe exit. The first condition of survival after splashdown is orientation. The capsule must become stable enough in the water for trained teams to come near it without making a dangerous situation worse. The ocean makes that stability conditional rather than automatic. NASA's landing and recovery weather criteria show that splashdown is governed not only by the capsule's performance, but by the sea state around it. Significant wave height, wind speed, cloud cover, and visibility all drive whether nominal recovery can proceed safely. For crew and vehicle recovery at the site, NASA specifies that there must be no precipitation or thunderstorms within 30 nautical miles. That significant wave height should be less than 6 feet, and that winds should remain under 25 knots to deploy the boats used in crew recovery. Yet Artemis II recovery planning also recognizes a harder truth. Because the mission returns from the Moon on a fixed broad geometry set by launch day and trajectory, Orion cannot simply wait in space for the calmest possible weather in the way some low Earth orbit vehicles can. NASA's recovery director explains that there is no station to undock from at leisure, and no easy loitering after lunar return while a better patch of ocean is chosen. The crew may therefore come down in conditions rougher and farther from mainland support than those typical of ordinary station returns. The nightmare NASA hopes never faces here is not only a bad splashdown, it is a technically successful splashdown in an ocean that still refuses to cooperate. This is why the recovery phase begins with caution rather than celebration. The capsule may look intact from a distance, but the water around it is not yet safe working space. NASA's recovery planning notes that debris fields and vehicle hazards must be understood before people move close. NASA explains that teams use trajectory and weather data to predict where descending hardware may fall and to decide how close recovery forces can safely approach at each stage. Even after that, this spacecraft itself remains a potential source of danger. According to NASA's recovery director, Orion is still powered when teams first near it, and ammonia may still be venting. Navy divers in the water therefore perform hazard checks, including sniff checks, before they do any work on the vehicle. NASA says this environmental safety check takes about 15 to 20 minutes after recovery authority is handed over from flight control to the NASA recovery director. Only then can the teams move from watching the spacecraft to touching it. The water landing has ended the flight, but not yet ended the spacecraft's ability to hurt the people sent to help. Once the scene is judged safe enough, recovery turns intimate and physical. NASA's current concept of operations does not keep the astronauts waiting inside Orion for hours while the whole capsule is brought aboard ship. Instead, Artemis II plans to recover the crew in open water first. The divers help the astronauts egress from the capsule onto what the team informally calls the front porch, and there The crew are fitted with recovery vests for helicopter hoisting. NASA describes 2 helicopters picking up the 4 astronauts in quick succession and carrying them to the recovery ship, where more personnel are waiting and medical assessment continues. Only after the crew is out does the focus return fully to the vehicle. Recovery personnel reconfigure the cabin, secure systems, close the hatch again, and then tow and guide the capsule slowly into the well deck of the military ship using a long line from a winch. The capsule is floated into the ship and brought to what the team calls hard down, meaning it is fully secured and cannot move. NASA's press kit adds that the mission goal is for the crew to be on the recovery ship within about 2 hours after splashdown. Water exit, helicopter transfer, shipboard care, and capsule retrieval must all happen in the right order, because the ocean punishes delay and confusion. Even here, at what appears to be the edge of homecoming, Artemis II still carries a web of contingency. NASA's recovery director says the team divides the work into recovery, rescue, and retrieval, because a nominal splashdown is only one possibility. Off-nominal landings, launch abort rescue, broken lines during shipboard retrieval, and parachute anomalies all sit inside a set of pre-planned decision criteria that NASA and its military partners rehearse repeatedly. That planning reveals the true nature of the splashdown region. It is not a ceremonial ending, it is a final operational struggle against water, motion, exposure, fatigue, and uncertainty after almost everything else seems finished. The astronauts may have survived launch, deep space, lunar flight, and re-entry, yet they still arrive inside a floating capsule in open ocean, dependent on divers, helicopters, ships, weather observers, and medical teams. NASA hopes this last region remains orderly upright airbags inflating as intended, hazard checks coming back clean, divers reaching the capsule on time, helicopters lifting the crew without trouble, and the ship drawing the spacecraft into its well deck with patient control. The nightmare it hopes never happens is that the mission reaches Earth successfully, but lingers too long in the unstable space between landing and recovery. Because on Artemis II, the ocean is not the place where danger ends. It is the place where danger must finally be managed all the way to the last hand on the hatch. At the level of the spacecraft itself, danger becomes a matter of boundaries. Orion survives Artemis II only because it carries its own interior world inside a small sealed body, and that body depends first on its outer structure. Before the crew can trust power, propulsion, software, or procedure, they must trust the shell around them. It does not look thick by the standards of ships, buildings, or underground shelters. It is a compact pressure vessel wrapped in layers of structure and protection, built to endure launch, vacuum, temperature extremes, radiation exposure, vibration, and the long strain of a mission that leaves Earth orbit and returns at lunar speed. The nightmare NASA hopes never faces at this level is among the simplest to describe and the hardest to forgive, a failure of the boundary itself. In ordinary life, pressure is quiet. Air presses on skin, walls, and windows constantly, and this goes almost unnoticed because the pressure outside and the pressure inside remain nearly balanced. A spacecraft changes that logic completely. Outside Orion, there is vacuum. Inside Orion, there must remain a breathable atmosphere for the crew. That means the structure must hold a persistent difference between the cabin and the surrounding emptiness. The crew module's shell is not merely a covering. It is a pressure vessel, a closed structure designed to contain internal air without letting it escape into space. Every square part of that vessel carries the burden of that difference. If the shell weakens, if a seal leaks, if a window fails, or if the hatch does not remain exactly secure, the spacecraft does not become uncomfortable, it becomes uninhabitable. This makes the outer structure one of the most unforgiving parts of the mission. A guidance error can sometimes be corrected, a communication problem can sometimes be worked around. Even a propulsion issue can sometimes be managed if time and geometry allow. A compromised pressure boundary offers much less mercy. The shell must remain whole from launch pad to splashdown. It must tolerate the shaking and bending of ascent, the quiet cold of deep space, the heating stresses of return, and the impact of water landing without ever ceasing to be a true enclosure. Orion's outer body is therefore not passive. It is always working, even when nothing appears to happen. The capsule may seem still against darkness, but its wall is holding life in minute by minute. The windows make this truth more intimate. A window in a spacecraft is not a simple opening made transparent. It is a structural decision. Orion carries several windows so the crew can see Earth, the Moon, stars, the outer vehicle, and parts of this mission environment. These windows support observation, orientation, and human awareness. But they also interrupt what would otherwise be an unbroken shell. Every window must therefore perform two roles at once. It must remain optically useful, and it must remain mechanically trustworthy. The material must tolerate pressure difference, vibration, thermal change, and the stresses that come with flight. A spacecraft window is a human desire built into a survival boundary. It allows sight, but it must never behave like a weakness. The nightmare here is not only a shattered pane, which is the extreme form everyone imagines. It is also a flaw too small to notice at first, a seal around the frame that does not remain perfect, a crack that begins under stress, or a surface strike that changes what the crew can trust. The hatch carries a similar burden, perhaps even more directly. Orion must be entered and closed before launch, and after that the hatch becomes one of the most important physical truths of the mission. It is the deliberate interruption in the pressure vessel that must stop behaving like an interruption and become, in effect, part of the wall. This depends on alignment, latching, sealing surfaces, and precise closure. On the ground, the hatch can be inspected, cleaned, checked, and verified by trained hands in the White Room before launch. In flight, it must simply remain right. The crew cannot treat it as a casual object. It is a door only before departure and after recovery. For almost the entire mission, it is a sealed barrier between life and vacuum. That gives the hatch a calm but severe status. It is ordinary in shape and extraordinary in consequence. Around these major openings and boundaries lie the quieter elements that make the shell trustworthy. Seals, fasteners, joints, interfaces, and penetrations do not draw the eye. Yet they often define whether a structure behaves as one body or many small risks tied together. A seal is a material or shaped surface that closes a gap and keeps a fluid from passing through. In Orion, seals help hold cabin air where it belongs and help prevent the intrusion of water or contamination where it does not belong. They are not dramatic technologies, they are disciplined ones. Their success is measured mostly by the absence of trouble. Yet in a spacecraft, the absence of trouble is one of the highest achievements engineering can offer. NASA hopes every seal remains invisible in the operational sense, meaning that it never announces itself by leaking, drifting, swelling, shrinking, or failing under changing temperature and pressure. The outer structure must also resist what moves through space with no warning. Small particles of natural dust and fragments of human-made debris can strike a spacecraft at very high speed. Not every strike is catastrophic, but every strike reminds the mission that emptiness is not perfectly empty. The shell must therefore combine lightness, because mass is costly in flight, with enough toughness to endure a harsh environment that includes not only vacuum and sunlight, but also impact risk. The crew may never know if tiny strikes occur. The structure must know. It must continue to hold pressure whether or not the surrounding space remains as clean as operators would like to imagine. Temperature acts on the boundary as well. One side of Orion can face bright sunlight while another side loses heat toward darkness. Materials expand and contract with changing temperature, and they do not all do so in the same way or at the same rate. This means the outer shell must preserve integrity while enduring repeated thermal contrast. The capsule cannot rely on one uniform climate outside. It carries its own climate inside while the outside shifts between extremes. The shell, therefore, does more than separate inside from outside. It mediates between two very different physical worlds and must keep doing so without warping into unreliability. So this region of Artemis II narrows the mission to its most basic physical promise. Orion is a small habitable interior carried through a vast uninhabitable exterior. And the truth of that promise rests first in the outer structure. Walls must hold. Windows must remain trustworthy. The hatch must stay sealed. Joints must behave as if they are permanent. The pressure vessel must survive every phase without yielding its burden. NASA hopes the shell remains so reliable that the crew seldom needs to think about it directly. That is the ideal form of success for a boundary. It becomes unremarkable because it never stops doing its work. The nightmare NASA hopes never happens is therefore stark in its simplicity. It is that the spacecraft's thin physical line between human life and open space ceases, even briefly, to be complete. Beneath the crew module sits the part of Orion that does much of the hidden work and receives much less of the public attention. This is the European Service Module, the machinery that follows the crew through deep space like a quiet second body, carrying the practical means by which the spacecraft moves, stays powered, remains thermally balanced, and continues to support life. If the outer shell of Orion is the boundary between survival and vacuum, then the service module is the support structure that keeps that survival meaningful over time. It is often described as the spacecraft's powerhouse, and the word is appropriate because the module does not serve one single role. It serves many at once. It provides propulsion. It generates electricity through 4 solar array wings. It contributes thermal control. It carries stores and systems that help supply water, oxygen, and nitrogen to the crew. It helps keep Orion pointed correctly in space. The nightmare NASA hopes never faces in this region is therefore not merely the failure of one machine. It is the weakening of the spacecraft's entire engine room. This makes the service module different from the crew module above it. The crew module is where people live and work. The service module is where much of the spacecraft's underlying capability is concentrated. It does not need to be habitable. It needs to be dependable. That difference gives it a severe kind of importance. The crew may look out through the windows and speak from the cabin, but the service module is the part that quietly turns a capsule into a functioning deep space spacecraft. Without it, Orion is no longer a vehicle that can travel around the moon and return by design. It becomes a sealed room cut off from the systems that let it behave as more than drifting mass. Propulsion gives the service module its most obvious authority. Once Orion separates from the rocket stages that launch it from Earth, the service module becomes the source of the main in-space maneuvering capability that shapes much of the rest of the mission. Its main engine performs the translunar injection burn that commits the crew to the moon. Its smaller thrusters provide orbital maneuvering, position control, and trajectory correction. The module carries a total of 33 engines, which reveals the layered nature of the task. Deep space travel does not depend on one heroic burst alone. It depends on a family of controlled forces, some large and some small, each used at the proper moment. The main engine changes destiny in a single burn. The auxiliary thrusters trim, steer, stabilize, and preserve the exact attitude needed for power, communication, and navigation. A spacecraft that loses all thrust is obviously endangered. A spacecraft that retains thrust but loses precise control can also become endangered, because deep space punishes pointing errors, mistimed burns, and slow drift. The nightmare here is not only silence from the engine bell, it is also misbehavior in the small emotions that keep a mission exact. Power is no less central. The 4 solar array wings of the service module unfold into space and turn sunlight into electricity for the spacecraft. This sounds simple in summary, but in practice it creates another chain of dependence. A spacecraft does not merely need sunlight in the abstract. It needs the correct orientation to gather that sunlight well. It needs the arrays to deploy and remain healthy. And it needs the electrical system to distribute the resulting power where it is required. This means propulsion and power are linked. The thrusters must sometimes keep Orion pointed properly, so the arrays can drink from the sun. The arrays then provide the electricity needed for avionics, communications, environmental control, lighting, and the broader life of the mission. If the arrays underperform, or if the spacecraft cannot orient them correctly, the effect is not limited to one subsystem. The weakness spreads. Batteries become more important. Margins shrink. Timelines tighten. A power problem in deep space is rarely an isolated inconvenience. It is often the beginning of a wider compression of safety. Thermal control deepens that same pattern. The service module helps keep the spacecraft at the right temperature, and this is one of the least dramatic and most necessary forms of survival. Space is not uniformly cold in the simple everyday sense. One side of Orion may face strong sunlight while another loses heat into darkness. Electronics produce heat of their own. Tanks, lines, valves, and structural materials all behave differently depending on temperature. Thermal control therefore means management, not one-directional warming or cooling. The service module must help prevent essential systems from drifting outside the narrow range in which they are reliable. A propellant line that warms too much, an instrument that cools too far, or a component that cycles repeatedly through extremes can turn a healthy mission into a fragile one. NASA hopes temperature control remains almost invisible, because when it succeeds, it disappears into normality. The nightmare is that it ceases to be invisible and announces itself through system stress, degraded performance, or a fault that spreads from one part of Orion into another. The module also carries life support commodities, and that gives its machinery a more intimate gravity. Water, oxygen, and nitrogen are not abstract provisions. They are the stored continuation of habitability. The crew module is where the astronauts breathe, work, and sleep. But the service module helps sustain the conditions that make such a cabin possible over the mission's duration. This does not mean the service module is merely a storage trunk. It means the crew's continued well-being depends partly on equipment outside the pressure vessel that must continue functioning through launch, deep space, lunar passage, and the return toward Earth. In that sense, the service module is both external and personal. It sits behind the crew, but it works in service of the breath, water, and environmental continuity that keep the crew from becoming a short-lived emergency. There is also a structural severity to the service module's role. It is not permanent. It must work faithfully for most of the mission, and then separate before Earth entry. That gives it a temporary destiny, unusual even by spacecraft standards. It is essential for propulsion and support, yet it cannot accompany the crew into the atmosphere. This means its attachment to Orion must be strong enough for deep space duty and clean enough for final separation. A module that cannot separate properly becomes dangerous at the end of a mission, even if it has served perfectly beforehand. A module that separates too early would be worse still, so the service module lives under a double demand. It must remain fully joined for as long as the mission needs its power and propulsion, and then it must leave without hesitation at the one point when the crew module has to become a different kind of spacecraft altogether. So this region of Artemis II narrows the mission to a body of hidden labour beneath the astronauts' feet and behind their backs. The European service module is propulsion heart, electrical source, thermal guardian, and carrier of essentials. It does not speak, and it is seldom the emotional centre of the mission. Yet it may be the clearest example of how a lunar voyage depends on machinery that is most successful when it is least noticed. NASA hopes it remains exactly that quiet, precise, and forgettable in the best possible way. The nightmare it hopes never happens is that this quiet machinery begins to fail in pieces, because each piece of the service module supports another, and together they form one of the most concentrated single points of dependence in the entire Artemis II mission. By the time Artemis II reaches the final descent hardware, the mission has already narrowed to a severe simplicity. The crew no longer depends on long-duration propulsion, on solar array pointing, or on the broad geometry of the lunar path. They depend instead on two linked forms of survival that work in sequence and cannot be exchanged for one another. First, the heat shield must absorb and survive the violence of return from lunar distance. Then the parachute system must take over and slow the capsule enough for splashdown to be survivable. This is why the region feels so unforgiving. The two systems do not work at the same time. They work one after the other, and the second depends on the first having brought Orion through re-entry in the right condition. If the heat shield fails badly, the parachutes never receive a healthy capsule. If the parachutes fail badly, successful re-entry still ends in a dangerous impact. NASA hopes the handoff between them remains almost invisible in flight. The nightmare it hopes never sees is that the spacecraft survives the hardest heat of the mission, only to discover that survival has not yet become safety. The heat shield exists because a spacecraft returning from the moon does not merely meet air, it collides with it at tremendous speed. Orion returns fast enough that the atmosphere ahead of the capsule compresses into a superheated plasma, and the outer surface of the vehicle must endure temperatures in the thousands of degrees. NASA uses an ablative heat shield for this reason. An ablative shield protects by sacrificing material in a controlled way. The outer avcoat layer chars, breaks down, and carries heat away as the capsule descends, rather than trying to remain unchanged. That design is calm in principle but brutal in operation. The shield is meant to be consumed in part, not preserved like polished metal. Yet this necessary sacrifice has limits. It must happen in the right way, at the right rate, and under the right internal conditions. The nightmare here is not simply that the shield gets hot. It is that the heat response ceases to remain controlled, and the shield begins to behave differently from the models and testing that were meant to predict it. Artemis I made that nightmare more concrete. After the uncrewed mission, NASA found unexpected char loss across Orion's heat shield. The agency later determined that gases generated inside the avcoat during the skip entry environment were not able to vent and dissipate as expected. Pressure built up inside the char layer, cracking occurred, and some charred material broke away in several locations. NASA's later investigation concluded that the spacecraft would still have kept a crew safe on that flight, and that temperatures inside the cabin remained within limits. But the finding changed the emotional meaning of the shield for Artemis II. It ceased to be an unquestioned inheritance and became a recently challenged system whose exact behavior had to be understood more deeply before people flew behind it. NASA's resolution was not to rebuild the entire shield for Artemis II. The agency stated that it could keep the Artemis II crew safe using the current heat shield with operational changes to entry. That conclusion is reassuring, but it is also revealing. It means that one of the final barriers between the crew and the heat of a lunar return now carries the memory of a real surprise from flight. The parachutes wait behind another boundary. During entry, the top of Orion is covered by the forward bay cover, which protects the parachute compartment from the heat of re-entry. Only after the crew module has passed through the harshest part of descent can that cover be cast off. NASA describes a layered parachute sequence that begins with 3 forward bay cover parachutes, working with pyrotechnic linear thrusters to separate the cover. Then 2 drogue parachutes deploy to slow and stabilize the capsule. After that, 3 pilot parachutes pull out the 3 large main parachutes that carry Orion through the last part of descent toward the ocean. This design reveals a quiet truth about the region. The parachute's not a single event, they are a chain. Each stage prepares the next. The cover must leave. The drogues must establish the right conditions. The pilots must extract the mains. The mains must inflate and remain healthy. If one part of the chain performs poorly, later parts inherit a worse situation. A parachute system is therefore not just fabric and cord, it is timed choreography under stress, and NASA has tested it across normal and failure conditions because return from deep space does not allow faith to replace qualification. The numbers make that severity easier to feel. NASA's Artemis II press material says the 2 drogue parachutes open at about 25,000 feet and slow Orion significantly before the pilot parachutes appear at about 9,500 feet to draw out the 3 mains. Those main parachutes are vast, each about 116 feet wide, and together they slow the crew module from about 130 miles per hour to about 17 miles per hour for splashdown. This is a profound reduction, but it is not gentleness in any ordinary sense. A spacecraft falling through the lower atmosphere after lunar return still reaches the ocean as a heavy object suspended beneath a system that must remain symmetrical enough, strong enough, and orderly enough to prevent dangerous rotation or overly hard impact. The nightmare here is not merely that no parachutes open. NASA's testing history shows a more realistic concern, one element of the sequence behaving late, weakly, or asymmetrically while the rest of the system struggles to compensate. Artemis II therefore places extraordinary trust in hardware that spends most of the mission packed away, unseen, and compressed into a compartment until the very last minutes. There is also a hidden relationship between the heat shield and the parachutes that makes this region even more severe. These systems are separate in function, but not fully separate in consequence. The forward bay cover and the parachute compartment sit on the same returning capsule that the heat shield must protect. If re-entry behavior becomes abnormal, the risk does not remain isolated to the underside of the spacecraft in an abstract thermal sense. It can spread through debris, structural loading, or altered descent conditions into parts of the vehicle that the parachutes depend on. This is one reason NASA took the Artemis I heat shield investigation so seriously. The problem was not merely cosmetic char loss on a test article. It was a signal that the final descent architecture of Orion must be understood as one connected survival system. A healthy parachute sequence depends on a crew module emerging from entry in the condition the parachute designers and analysts expect. A healthy heat shield matters not only because it keeps fire out, but because it delivers the right spacecraft to the next mechanism in line. The nightmare NASA hopes never happens is therefore a bad handoff. A spacecraft descending out of plasma with just enough hidden damage or unexpected behavior to make the parachute's job harder, at the one point where recovery of lost margin becomes most difficult. So this part of Artemis II becomes the last test after almost everything else has already gone right. Orion must survive the heat of lunar return with a shield that now carries the lessons of Artemis I. It must then throw away the cover protecting its parachute bay, deploy each stage of the descent system in the proper order, and arrive at the Pacific not merely intact, but slow enough to be recoverable. NASA hopes this entire region feels simple when seen from afar: a glowing return, a successful blackout, parachutes blooming high above the ocean, and a capsule descending steadily towards splashdown. Yet beneath that apparent simplicity is one of the sternest truths in the mission. At the very end, after the moon has been passed and Earth has already been reached, survival still depends on whether sacrificial material burns as expected and whether folded cloth awakens exactly on time. Inside Orion, survival becomes a matter of balance held inside a very small volume. NASA describes the crew module as having about 330 cubic feet of habitable space, roughly the volume of 2 minivans. And that smallness is part of the danger rather than a neutral design fact. A small cabin is easier to control in some ways, but it is also quicker to change for the worse. Every breath alters it. Every meal, every movement, every rise in body heat, every bead of moisture in the air, and every failure of circulation or removal shifts the environment the crew depends on. This is why Artemis II treats the cabin atmosphere and water supply as one of the central things the mission must validate in flight. NASA's official objectives for the mission explicitly include checking out Orion's life support system under real metabolic loading, monitoring the atmosphere inside the crew module, performing meal preparation and waste disposal, demonstrating depressurization and repressurization capability, and validating crew survival procedures. The quiet nightmare in this region is not a dramatic explosion or a visible structural break. It is the loss of controlled balance inside a cabin that must remain livable minute by minute because the crew has nowhere else to go. Orion's environmental control and life support system is built to manage cabin temperature, pressure, humidity, oxygen, carbon dioxide, water, and waste altogether because these are not separate comforts. They are one closed human environment. Pressure must remain high enough and stable enough for human bodies and equipment to function normally. Oxygen must be present in the right amount, not merely available somewhere in storage. Carbon dioxide must be removed as quickly as the crew produces it, because in a closed cabin the problem with breathing is often not the absence of oxygen at first, but the accumulation of the gas just exhaled. Humidity must also be controlled, because air that grows too wet affects comfort, condensation, electronics, and the long, quiet fatigue of living in a sealed place. Temperature must stay within a narrow band, especially in a spacecraft where heat from electronics, sunlight, exercise, and human metabolism has no ordinary weather to disperse it. Water must remain available for drinking, food preparation, and basic medical use. Even though every kilogram launched away from Earth matters, the cabin therefore becomes a managed ecosystem, but one made of tanks, valves, sensors, ducts, controllers, and procedures rather than soil, rain, and open air. NASA's more recent Orion material describes a regenerable air system that removes carbon dioxide and humidity while conserving mass and volume. And the detail matters because regenerative removal means the system is meant to keep working rather than be consumed quickly like older one-use absorbent canisters. In NASA's own Artemis II spacecraft discussions, the component watched most closely is the carbon dioxide humidity controller, a set of 3 regenerative units that act like molecular sponges, pulling carbon dioxide and water vapor from the cabin air and then releasing them overboard during regeneration. That system is one of the most revealing examples of cabin fragility. If it works, the air remains quietly acceptable, and the crew may think little about it. If it falters, the spacecraft begins to change from habitat into threat without any need for fire or rupture. Carbon dioxide can rise invisibly, moisture can build, crew performance can degrade, small symptoms can become judgment problems, and judgment problems inside a spacecraft can multiply every other risk. NASA has been careful enough about this that Artemis II carries contingency lithium hydroxide canisters, an older non-regenerative method of carbon dioxide removal, specifically so the crew could be brought home safely if the new hardware did not behave as intended early in the mission. That backup tells its own story. Orion's cabin is advanced, but it is not trusted casually. Water introduces a second form of dependence that is quieter but just as intimate. Orion's potable water dispenser is supplied from 4 pressurized tanks in the service module and is used to rehydrate food, prepare drinks, and support medical needs. This means the crew's water is not simply carried as a passive reserve in bottles scattered around the cabin. It is part of a system, delivered across a spacecraft that must keep lines, connections, and valves trustworthy while everything else in flight changes around them. NASA's public Orion descriptions also make clear that the crew module relies on water tanks and a dispenser as part of ordinary daily living, and that the same environmental system which keeps oxygen and pressure in range also removes excess heat, humidity, and even odor during exercise. That last detail matters because Artemis II is not a short launch and land stunt. The astronauts are expected to exercise daily, and exercise deliberately increases metabolic loading by raising breathing rate, carbon dioxide production, moisture, and heat. In other words, one of the ways NASA protects the crew's long-term health also makes the cabin work harder, and the cabin must prove it can keep up. There is also the problem of contingency. Orion's crew survival suits are designed to provide pressure, oxygen, and thermal protection during launch, entry, and certain emergency cases, but those suits are not substitutes for a failing cabin. They are layers of protection around vulnerable bodies inside a vehicle that is still expected to maintain oxygen, water, temperature, and crew health as its normal state. Artemis II training and mission objectives show that NASA treats emergency donning, repressurization, fire response, and related cabin procedures as serious tests rather than mere drills. This reveals the deepest truth of the region. The interior life support balance is not just an engineering success condition. It is the line between routine life in space and a medical emergency that begins with the air itself. In the open world, a person can leave a room that feels wrong, open a window, step outside, drink from another source, or wait for help in breathable surroundings. Inside Orion, none of those ordinary escape routes exist. The crew lives inside a managed atmosphere that must remain correct because correction is the only alternative to decline. NASA hopes this region remains almost boring in the best possible way the air circulating is designed. The carbon dioxide scrubbed away, the humidity controlled, the water dispenser working, the temperature steady, the meals prepared, the waste removed, and the cabin atmosphere monitored without surprise. The nightmare it hopes never happens is that something inside this small closed world drifts outside balance. because in a spacecraft the first sign of danger may not be noise or flame, but the slow corruption of the very air and water that keep 4 human beings able to think, work, and stay alive. Inside Orion, danger can arise not only from heat, vacuum, or hardware wear, but from information itself. A spacecraft moving through lunar space must constantly know where it is, how it is oriented, what its systems are doing, what the crew is commanding, and which signals can be trusted at any given moment. This makes the flight computers, displays, sensors, and crew procedures one of the most delicate inner regions of Artemis II. Orion is not flown by instinct. It is flown by layers of software, data handling, guidance logic, communications links, cockpit displays, hand controllers, and disciplined human interpretation. The nightmare NASA hopes never faces here is not a simple loss of power or a broken wall. It is the moment when the spacecraft still has most of its physical capability, yet the crew and the machine begin to lose shared understanding of what is true. That risk begins with complexity. Orion's avionics do not perform one task. They connect many tasks that must remain synchronized. Flight computers receive information from sensors, compare it with expected behavior, command other subsystems, manage timing, and support guidance, navigation, control, and communications. The cockpit then presents that invisible work informs the crew can use glass displays, status pages, alerts, cues, and control interfaces. This sounds orderly, and ideally it is. Yet order in a spacecraft depends on thousands of small acts of agreement. The sensors must measure correctly, the computers must process correctly, the displays must present correctly, the crew must interpret correctly. When all of those steps align, Orion feels manageable. When even one of them begins to drift, the entire spacecraft can become mentally heavier. Redundancy exists because NASA understands this. Orion does not rely on one single flight computer thinking alone in the dark. It carries multiple redundant computing paths so that one fault does not immediately become loss of control. Redundancy is a design choice that means backup capability exists alongside the primary one, allowing the spacecraft to continue functioning if a component fails or produces suspect data. This protects the mission, but it does not make the mission simple. A redundant system must still decide which source is healthy, which disagreement matters, and how to pass authority without introducing new confusion. A backup is only useful if the spacecraft and the crew can identify when it should be trusted more than the first answer. That is why software faults and sensor disagreements are so dangerous in human spaceflight. They do not always arrive as silence. They can arrive as competing confidence. Navigation deepens this problem. Orion must know its position and attitude in Earth orbit, on the way to the Moon, near the Moon, and on the way home. It uses different tools in different parts of the mission, including navigation aids near Earth, star-based sensing, onboard guidance logic, and tracking from the ground. These methods overlap to strengthen the spacecraft's sense of place, but overlap can also create a new burden. The crew and flight controllers must know which source is leading, which source is confirming, and what it means when one source departs slightly from another. A major navigation failure is an obvious danger. A subtle navigation mismatch can be more deceptive. It can let the mission continue while quietly spending margin in the wrong direction. The hand controllers inside Orion reveal how tightly software and human action are joined. Artemis II includes manual flying tasks because NASA wants real astronauts to evaluate how the spacecraft handles when humans, not only automation, command small motions. During proximity operations, The crew uses translational and rotational hand controllers to make careful movements relative to the upper stage. These controls look direct in concept. A hand moves, and the spacecraft responds. But the response is never purely mechanical. Orion's software interprets the command, decides which thrusters to fire, and manages the pulse timing needed to create the requested motion. This means manual control in Orion is not the opposite of automation. It is a partnership with automation. The nightmare here is not only a hand controller that fails to respond, it is a system that responds in a way that is slightly different from what the crew expects, especially when the crew is close to another object and small movements matter. Displays are part of that same partnership. A spacecraft cockpit must do more than show data. It must show the right data at the right moment, in a form that can be understood quickly under pressure. Too little information leaves the crew blind. Too much leaves the crew buried. If pages are hard to navigate, if priorities are unclear, if a caution message is accurate but badly timed, or if several minor alerts arrive together and compete for attention, workload can rise faster than the physical emergency itself. This is one reason Artemis II remains a test flight. NASA is not merely proving that Orion can move through space. It is learning how the spacecraft feels to operate with humans aboard. A cockpit can be technically correct and still become dangerous if it asks for too much interpretation at the wrong time. Communications add another layer of dependence. Orion must exchange voice, telemetry, commands, and tracking information across changing operational environments. Early in the mission, there is a planned handover from near-Earth communication support to the deep space network. Later, the spacecraft must endure expected communication gaps, including the loss of signal behind the moon and the blackout during re-entry. These intervals are understood in advance, but understood silence is still silence. Outside those expected gaps, the mission depends on a flow of information between spacecraft and ground that must remain timely and trustworthy. If telemetry becomes incomplete, if command pathways narrow, or if a communication mode behaves differently than expected, then the crew and mission control can begin working from different pictures of the same spacecraft. Artemis II also plans to demonstrate optical communications capability, which shows that even communication itself is part of the mission's test agenda rather than a background certainty. Crew task load is therefore not a minor concern. Orion does not ask the astronauts merely to sit inside a safe vehicle while the systems do everything for them. The crew checks spacecraft performance, flies test objectives, manages displays, evaluates handling qualities, executes procedures, and stands ready for emergency responses including fire procedures, medical procedures, rapid suit donning, and radiation shelter actions. A spacecraft becomes more dangerous when tasks stack faster than attention can sort them. One caution light can lead to a page call-up. That page can demand a cross-check. The cross-check can require a conversation with the ground. The conversation can be interrupted by another system queue. None of these steps is dramatic alone. Together they can compress time and narrow judgment. The nightmare NASA hopes never happens is that Orion remains mostly alive and mostly functional, while the crew is forced into procedural overload, because overload can turn solvable anomalies into escalating ones. So this region of Artemis II is not made of metal or flame, it is made of awareness. Flight computers must remain reliable, sensors must remain believable, displays must remain clear, hand controllers must produce the motions the crew expects. Communications must preserve a common picture between Orion and Earth. Procedures must guide action without burying it. NASA hopes all of this inner machinery remains quiet enough that the astronauts can work with confidence and measure the spacecraft rather than struggle to understand it. The nightmare it hopes never happens is that the mission begins to drown not in vacuum or heat, but in ambiguity, because a deep space spacecraft can survive many physical hardships if knowledge stays intact, and can become dangerous very quickly when knowledge itself begins to break apart. At the center of Artemis II, after the weather, the launch tower, the atmosphere, the vacuum, the moon, the heat shield, the cabin air, and the computers, there remain only 4 human bodies. Everything else in the mission exists for them or because of them. The rocket is not the point. The spacecraft is not the point. The mission architecture, however large and intricate it becomes, narrows in the end to a simple biological fact. 4 people leave Earth carrying organs that require oxygen, water, heat balance, sleep, orientation, judgment, and a narrow range of physical stability. Spaceflight often appears mechanical from the outside because machines dominate the image, but the innermost region is not mechanical at all. It is flesh inside pressure suits, blood in shifting fluids, bones and muscles in weightlessness, eyes and inner ears trying to agree about motion, and minds attempting to remain calm while the body passes through environments for which it did not evolve. The nightmare NASA hopes never happens at this level is not only the failure of equipment, it is the point at which the body itself becomes the mission's weakest system. Microgravity begins this process quickly. In ordinary gravity, fluids settle downward through the body in familiar ways. In weightlessness, that pattern changes. Fluid shifts upward toward the chest, head, and face. Astronauts often appear puffy in the face for this reason, while the legs can look slightly thinner than normal. This is not merely cosmetic. Fluid redistribution changes how the body senses itself and can contribute to congestion, altered pressure sensations, and a general feeling that the body's internal map has been rearranged. The crew does not step into weightlessness as if entering an empty room. The body reacts to it. The heart and blood vessels begin adjusting to a new fluid pattern. Balance cues change. The familiar downward reference that shapes standing, reaching, turning, and sleeping disappears. Artemis II will not be a long mission by the standards of future Mars plans, but even a relatively short mission can become physically difficult if adaptation comes slowly or unevenly. Motion sickness is one of the clearest examples. The inner ear helps the brain understand motion, and in weightlessness its signals can conflict with what the eyes report. The body is moving, but not in the familiar ways gravity-trained instinct expects. This can produce nausea, disorientation, headache, and reduced effectiveness, especially in the first days. Such sickness is not a trivial discomfort inside a spacecraft. It can interfere with eating, sleep, concentration, procedure execution, and the basic steadiness needed for test work. Artemis II is a test mission, which means the astronauts are not simply passengers enduring a voyage. They are expected to evaluate systems, perform tasks, conduct observations, and manage themselves as operators. A crew member who feels unwell is not merely suffering privately. That unwellness enters the mission as degraded human performance. NASA trains for this, monitors it, and plans workloads accordingly. Yet training does not erase biology. The body's first response to space may still be confusion. Fatigue deepens that danger. Spaceflight compresses time in unusual ways. There are checklists, communications, suit operations, meal periods, maintenance work, observation tasks, public events, exercise sessions, medical monitoring, and the constant low-level awareness that every action occurs in a sealed vehicle very far from easy help. Even when no emergency occurs, the mind remains active under constraint. Sleep in such an environment is therefore not just a biological need. It is an operational requirement, yet sleep can be harder than it sounds. Noise from ventilation and equipment continues in the background. The body lacks ordinary signals of day and night, excitement, stress, schedule shifts, and the strange physical feeling of floating can interrupt rest. If sleep quality declines, judgment declines with it. Small interpretation errors become more likely, patience becomes thinner, memory becomes less reliable. A tired crew in deep space may still function, but it does so while quietly spending one of the most precious margins any mission has. Radiation adds a burden that the body may not feel directly in the moment. Unlike motion sickness or fatigue, radiation often does not announce itself as immediate pain, yet the body still receives it. Artemis II will carry the crew beyond Earth's broad magnetic protection, and that means the astronauts are exposed to a harsher environment than crews in low Earth orbit. Most of the mission will likely pass without any severe event, but the biological reality remains. High-energy particles pass through tissue and can damage cells. The body does not negotiate with this by willpower, it endures it. NASA can monitor dose, use shielding, track solar conditions, and direct the crew toward better protected configurations if needed. But the crew still travels as living tissue through a region where exposure is real. The nightmare here is not only a major solar event, it is the larger truth that the human body in deep space remains biologically vulnerable, even during a mission that seems outwardly calm. Confinement shapes the mind as much as the body. Orion's habitable volume is small, and 4 people must share it through launch, cruise, flyby, return, and recovery. There is little privacy, there is little distance. Every movement matters because someone else is near. Every object has a place because loose disorder becomes operational trouble. In such an environment, temperament becomes part of mission safety. A crew cannot afford unnecessary friction. It must remain cooperative, precise, and emotionally steady. This is one reason astronauts are chosen not only for technical competence, but also for judgment, discipline, and the ability to function well with others under stress. Even so, selection does not make them less human. Irritation, worry, disappointment, and mental overload remain possible. The deeper danger is not argument for its own sake. It is the gradual narrowing of emotional resilience in a small sealed world where the next task still has to be done correctly no matter how anyone feels. The body also resists inactivity, and that gives Artemis II another quiet challenge. In weightlessness, muscles and bones no longer carry the same loads they carry on Earth. Over time, this leads to deconditioning, which is why astronauts exercise in space. Even on a shorter mission, movement matters for circulation, strength, and general health. Yet exercise in Orion is not casual recreation. It raises body temperature, breathing rate, sweat, and carbon dioxide production inside a small cabin already responsible for controlling all of those things. So the human need to preserve physical function feeds back into the spacecraft systems that must support that effort. The crew protects the body by working the body, and the spacecraft must absorb the consequences. Dehydration, nutrition, and waste management seem less dramatic than launch or re-entry, but the body treats them seriously. A person who drinks too little, eats poorly, or falls behind on basic bodily care becomes slower, less clear-headed, and more fragile. In space, Appetites can change, taste can feel different, and mild sickness can make regular intake less appealing. Yet the body still requires water, salts, calories, and routine. Artemis II therefore depends on ordinary acts being done well under extraordinary conditions. The nightmare at this level is often cumulative rather than sudden. A little nausea, a little dehydration, a little fatigue, a little mental strain, and a little loss of appetite can join into a crew that remains technically healthy while becoming operationally weaker. So the mission closes around the astronauts in the most literal sense. Weather can be managed, hardware can be inspected, software can be patched before flight, trajectories can be calculated. But once Artemis II begins, the final measure of success is whether 4 human bodies can remain stable enough, rested enough, nourished enough, protected enough, and clear-minded enough to live through the mission and perform their work inside it. NASA hopes this innermost region remains almost invisible, meaning that the crew adapts well, sleeps well enough, eats, drinks, exercises, thinks clearly, and reaches home without the body becoming the main source of uncertainty. The nightmare it hopes never happens is that after all the mission's engineering has done its part, the oldest and softest thing in the spacecraft proves to be the hardest thing to protect. The mission ends where all long journeys end, not in triumph as a sound, but in stillness as a condition. The ocean settles around the recovered capsule. The hatch opens. Outside, air moves across faces that have lived for days inside a managed atmosphere, and gravity begins its old work again. The body feels weight not as an idea, but as a return of pressure through legs, spine, and inner ear. What has been held in careful balance by tank, seal, software, fabric, and procedure now gives way again to the larger balances of Earth. Salt air, wind, light, distance, and ordinary breath reclaim their place. From the outside, Artemis II can be described in engines, miles, burns, shields, trajectories, and recovery timelines. From the inside, it remains something smaller and quieter. It is a brief removal of human life from the world that formed it, and a careful effort to return that life intact. Every nightmare scenario NASA hopes never happens exists because the mission is real. Real flight leaves the ground. Real bodies tire. Real machines drift, heat, seal, vent, ignite, and endure. Real oceans move under returning spacecraft. None of this makes the mission bleak. It makes it exact. The deepest truth of the flight is not that space is hostile in some theatrical way. It is that life is narrow, and the region in which human beings remain comfortable and safe is thinner than it first appears. Artemis II carries 4 people beyond much of that natural safety, surrounds them with engineering meant to extend it, and trusts discipline to close the remaining gap. When the mission works, the drama disappears into procedure. The danger remains present, but it remains managed. The capsule floats. The crew returns. The systems fall silent one by one. Earth takes them back without needing to explain itself.